Okay, let's get into chapter two. So, chapter two is all about sets and set notation and unions and intersections, subsets. Unfortunately, the first one or two sections are very definition heavy. So, the PowerPoints have quite a few slides, but the slides aren't very difficult problems to go through. So, we're going to go through these definitions so we can kind of set things up for sets later on. And sets are used throughout mathematics. It is definitely in the category of things that I still talk about today in my PhD program. We talk about sets all the time. We use these definitions. So they are pretty universally used. And so here's a very basic way to write a set. We typically give a set a name, kind of like with function notation. It's usually a capital letter, could be capital S or capital A, kind of comes around a lot. And then we list elements. And so sometimes they're numbers, like this case. They could be like states in the country. They could be colors. They don't have to be strictly a mathematical number or an operation. And that's essentially the only restriction on it. Like, there doesn't have to be order. Like in this case, I have 1, 2, 5, 9, 3. It doesn't have to only be numbers, and or sorry, it doesn't have to be all the same thing. Like I could have numbers, and then I could also have months in my set. It's only really the idea is that we're talking about a group of things. So here's a basic example of a set. There's ways to write sets. Sometimes we list them. That happens quite often because we might only be talking about 3 or 4 items. Or even really if there's a million items and they follow a really nice pattern, sometimes we can still write it just as a basic list. Like if we're talking about all the numbers we can count, 1, 2, 3, we would write it like we have above, just with a dot, dot, dot at the end to say, oh, my set goes on and on and on. But another way we can write sets is we can kind of describe them. And so sometimes if the pattern isn't super evident, we kind of have to explicitly write what the pattern is of our set. And so here it's called a, I think, roster method I've heard set builder, notation. But essentially it all just boils down to you say that we have brackets, we're talking about our set. In this case, our set is A. And then we say, here's my variable for my elements. I'm talking about my X, or I'm talking about my X comma Y if I want to talk about like points or something like that. And so then I write what I'm talking about, what I want to describe, and then I put a bar, a vertical bar, which generally translates to such that, and then I describe what that element is. So in this case, my set are the elements are X, such that X is a month that begins with the letter M. So that's set builder notation, and in this case, it's actually much nicer to write the list notation. So let's write what that is. That's what this translates to. Think about all the numbers or all of the months, and I look at the specific months with the letter M, and those make up my set. So yeah, it seems silly to even talk about roster method as I mentioned here, because there's only 2 months that meet that criterion. So we might as well write them. Where if we want to start to talk about like, I don't know, all of the prime numbers, it's kind of hard to write that as a list because that goes on forever and ever and ever. And even if I write the first, I don't know, 8 terms, if you didn't know I was talking about prime numbers, it would be dangerous for me to write dot, 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 because you might not know what the rest of the stuff is. Where if you wrote the set A is equal to X such that X is a prime number, then it is very clear that, okay, we're talking about the set of every single prime number. I get it. Now we can start to do things about the set. We can talk about what's in the set versus what's not in the set. There's also a possibility that there's nothing inside our set. Like if we wanted to talk about our set builder notation and we say our set A is all X such that X is a month that begins with a letter Z, well, there's nothing in that set. And so we could write just empty brackets, which is a pretty good way to indicate that we're talking about a set with nothing in it. Or kind of more often what we see in higher level mathematics is this 0 with a slash through it. It's just called the null set or the empty set, which is just there's nothing in it. Now another symbol or definition is this kind of weird shape E. It's almost a capital E, but smooth instead of sharp edges on the left side. And so we say an element is in our set by using this E. And if an element is not in our set, we use this E with a slash through it. So example here, if I want to talk about the list of natural numbers, and this is a very common list that's used, so we write it as capital N as a set, or sometimes we write it as, let's see if I can do this nicely. Sometimes we write it like this, but it's a set we reference so often that it kind of gets its own fancy number N, like the integers get a fancy letter, capital Z like that. Again, maybe this is a dangerous thing to do. These are turning out pretty good. So anyways, if we're talking about the set of all of the natural numbers, and then I guess I want to clear this. And then we want to talk about whether or not an element is in the set of natural numbers. Well, natural numbers also are called the counting numbers, because if we were to start counting, I don't know, like a basket full of apples, we wouldn't start by saying 0 and then count 1, 2, 3, 4. If we're counting, we typically start at 1, and we could go on for, I mean, potentially forever and ever and ever, but that's why we're calling those, or that's why they are called the counting numbers, is that that's how we would count things, I guess. I don't know. I'm trying to be a little bit more fancy about it. And so if we're going to use this notation, I could talk about numbers that might be in my set or might not be in my set. And so if I were to write -1, well, -1 is clearly not in my set of natural numbers based on that description. So I would write -1 is big E, not in my set of natural numbers. Or if I wanted to talk about an element that was in my set, I could write 5. We can see right there in the actual definition of natural numbers that is in our set. So if we wanted to use our symbols, we would say that 5 is in our set. So smoothie with a slash through it means it's not in that set. Biggie or smoothie, capital E with smooth edges means that that element is in that set. And so to do a couple more examples of this set builder notation that I did on the first slide, if I wanted to write all of the numbers such that x is a natural number and x is less than 4, because I can use as many descriptors as I want. It doesn't have to just be one descriptor, like the months that start with, I don't know, I think it was the letter M. So if I want to talk about the natural numbers that are less than 4 and it is strictly less than 4, then I would list 1, 2, 3. I want to talk about the natural numbers that were strictly greater than or equal to 4. Here's what I was kind of talking about on the first slide. Well, 4 is strictly, or not strictly, greater than or equal to 4. 4 is greater than or equal to 4. So is 5. So is 6. And we could play this game forever and ever, but eventually we start to get the pattern that it's the natural numbers. And so we write this 3 dots saying this is going to go on forever and ever and ever. And then we could say x is a natural number and it is strictly between 4 and 8. So we don't list 4, we don't list 8, it would just be 5, 6, 7. Cool. Another thing pretty common, and the notation in the book honestly isn't what I typically see for cardinality. So I guess actually at CU Denver, I am kind of seeing this notation a bit more. But when I was an undergraduate, I also saw this for cardinality. And so what cardinality is, as far as a definition, is just how many items are actually in our set. And so we can sometimes count that number, sometimes it's infinity, but it's just telling us exactly how many elements are there so that we could start to, I don't know, do things to our set. like kind of going back to probability where we had this issue of listing all of the possible values, like flipping a coin, heads, tails, tails, heads. The cardinality would be how many total things were in our sample. So it's just the total number of items in our set. And so sometimes that's represented as a lowercase n, sometimes that's represented what I wrote in red over here with like almost an absolute value. And so just as an example, if we look at the set A in our ABCD, there are 4 elements in that set, right? 1, 2, 3, 4. For question B, there is 1 element in my set. It's not the actual values, right? So 0 is the single element in my set B, but as far as how many items are in my set, there is 1, a single 0. And then for C, we could sometimes have it listed out kind of poorly like this with dots. And so we might have to be a little bit clever about how to calculate the items in the set. We could count up and go 13, 14, 15, and kind of keep track maybe with a tally or something like that. Or if there's bigger things going on, like talking about odd numbers between 1 and, I don't know, 30, we might have to be a little bit careful, but we would, developing formulas is pretty common for finding cardinality. So I think that answer is, it's either 10 or 11. But the purpose of that example is to sometimes it's not as easy as straight up just counting the things in the set. And then for D, that is the symbol for null set. Well, we talked about the definition of null set already. It means that there is nothing in my set. And now we kind of get into a little bit of, or a couple of murky definitions that I'm also not crazy about how the book defines. They start to talk about this idea of equivalent sets. And if you read the book at all, they kind of poorly define what that means. I think their definition is just that the cardinalities are the same, which I don't think is true. I don't know, maybe they're using a different definition than the one that I'm used to. But what we do talk about when we talk about kind of, I don't know, equivalent sets, again, I don't love their notation of the equivalent sets, is sometimes we talk about this idea of one-to-one correspondence. That is something that is correct and I agree with. And that's if we have 2 different sets that have the same cardinality, and we can talk about how to kind of relate one to the other, then we do say there is a one-to-one correspondence between those 2 sets. And so a good example, like let's say I have the set 1, 2, 3 as my A set, and my B set is 2, 3, 4. Then I can make a one-to-one correspondence between these 2 sets by saying, okay, the sets in B are all the elements in the set of A, just with 1 added to them. I suppose maybe I should write that out. So let's say my A is equal to 1, 2, 3, and my B is equal to 2, 3, 4. Then there is a one-to-one correspondence of, if I add 1 to every element in my set A, I would get an element in my set B. So that is an important mathematical concept of, can we relate these 2 sets, and is there really a nice relation to describe these 2 sets, or maybe I shouldn't be able to do this and I can't really claim that the 2 cardinalities are the same. I would say that definition is probably the hardest thing in the section, and I don't think we're going to linger on that one too much, where on everything else up to this point, if we're talking about the natural numbers, we'll talk about those again. If we talk about the null set, we talk about whether or not an element's in there or an element's not. So make sure you're super comfortable with those. Maybe one-to-one correspondence, a little bit less so. And then finally, 2 sets can be equal, right? I think I said it on the first slide, they don't have to be ordered in any specific way. I could write a set as 1, 2, 3, 4, or I could write a set as 4, 3, 2, 1, and those 2 sets are equal because A, they have the same cardinality, but B, they also have every single element the same. So in this case, we have set A and set B. They have the exact same elements. Sure, the elements are in different order, and we kind of see these color relationships between the 2. But that's not really important. It's that all of the elements in A are elements in B, all the elements in B are elements in A, and the cardinality is the same. So, I mean, the truth of the matter is this doesn't really happen too often. So there aren't a lot of really cool, interesting traits about equal sets, but it can happen, and that happens when specifically all the elements are the same and the cardinality is the same. Which I guess if all the elements are the same, the cardinality has to be the same. And then I guess the last thing that sneaks into the middle of this slide is this idea of finite and infinite. And infinite is probably what you would think it is. It means that if I have a set that is infinite, that it goes on forever and ever. So the natural numbers are infinite because we could count up to 1,000,000 and then another 1,000,000 and then forever. And so it's a set that goes on forever. Where finite is, that's also a really wordy definition. A finite set is just that it kind of stops at some point. So if you can count, and maybe it takes a while to count, but if you can count all the elements in your set, and you would eventually stop at a certain number, it's finite. So A and B are finite. The months that start with M are finite. The numbers between 1 and 7 are finite because you could give me a number for the cardinality. You would say there is 2 elements in that set, or 20, or if there's even 1,000,000 elements in that set, that is finite as long as my set stops. It doesn't go on forever and ever. So that's also kind of technical definitions. I might pull out that term here and there, but just remember, finite means that it stops, it has a certain number of it. Infinite means there's infinite amount of things in them. That's it for this section.